Hi, welcome back. In this video, we're going to talk about circles. Now, this is going to be the beginning of our circles unit. So we're going to introduce a few key words of how do you identify parts of a circle, how do you name it, and then we'll get into a bit of a review with circumference, back from middle school, maybe even elementary, and extend some of these to make connections with the concepts that we have spoken about in this class already. So high school geometry mixed with some middle school, elementary review. Let's get going. As you can see here, we're going to use this circle for an example. We have a lot of segments. We have A, B, D, E, O, C. We have all kinds of different parts to the circle. So as an introduction, let's start with some vocabulary. So first we want to address the different segments in a circle. Let's start by the definition of a circle, right? So here we have the word circle. A circle is a set of all points in a plane that is equidistant from the center of a circle. Basically, we have a center, and then any point on the circle will be the same distance to that center. Right? If I look at all these lengths, that length, that length, that length, that length, any point on the circle will be equidistant to C. So the name of the circle, we can call it a dot with a circle around it, circle C, which is the name of the center. Or in long terms, we can say, or circle C, right? We're used to using symbols here in math, so we're going to use the circle with a dot inside of it. Now, a segment that has two endpoints, right, at the center and on the circle, if one of the points is the center and one of the point is on the circle, right, like CE, we have CF, and even CD. We call that the radius. And for plural, we call it radii. We have more, of course. We have CB, we have CA, we have more radius, or more radii here in the circle. The next word is chord. A chord is a segment with endpoints on a circle. So endpoints really just means that the 2 points on that segment are going to be on the circle. So an example, AB is a chord. I could even create one DF. As long as both endpoints are on the circle, they're considered chords. So technically, if it goes through the center, this is also a chord. Now we know if it goes through the center, a chord through the center is actually known a diameter. So here's where we can write the last word that we're dealing with is diameter. So diameter is really just any chord that goes through the center. As you can see here in the bottom, these are some of the formulas we're going to be using, where circumference is pi times diameter, or since the radius is 2 times the diameter, we can call that 2 pi r for circumference. Okay? Now, some of these formulas that we might be using are the midpoint formula and the distance formula, and even the Pythagorean theorem. These are the high school components that we're going to bring into the middle school review component. So let's do some examples. I'll leave some of the formulas here. First, we want to find the circumference given the following information. So circle A is centered at 2, 3, and it goes through the origin. So if I were to do a graph here, I'm going to draw a graph. Let's start with an x and y plane. It's centered at 2, 3, so 1, 2, 1, 2, 3. That's the point. It's centered there, so I know that's the center of a circle. We're going to call that point A. And it goes through the origin, which means I have a circle here that goes through the origin. Therefore, if you can imagine, so I can draw this a little better. If you can imagine a circle, this is not a circle, it's more like an oval. If you can imagine a circle that goes through the origin and is centered at 2, 3. So we want to find the circumference. So the formula for circumference is 2 pi r. This is the one that we're going to use since we're given the radius here. We can actually find this radius. If we find that radius, we can use the formula circumference equals 2 pi r. One way to do this is we can actually build a right triangle here, and we can use Pythagorean theorem to find the length of the radius. Right? This value here, we can use the length of 2 and the length of 3, and we can do Pythagorean theorem. If I blow this triangle up a little bit, I'm trying to find the length of the radius, which would be c. We know the two sides. So Pythagorean theorem says 2 squared plus 3 squared equals c squared, which is r squared. If I simplify, I have 4 plus 9 equals c squared. 4 plus 9 is 13. So that equals to the radius squared. I square root both sides. The radius for this problem would be the square root of 13, about 3.61. Now, that's our radius. Now that we know the radius, the formula is 2 pi r, so we're going to plug that in here. Circumference equals 2 times pi, which we can use the calculator button as pi times the radius, 3.61. And that would give us a circumference of 22.68. There we go. All we're doing here is we're mixing in what we know about Pythagorean theorem with circles in the same context. But again, if we have the picture, we should be okay. Let's look at the second scenario. We have circle A has opposite points on the circle B and C. So let's graph this real quick. Let's draw a quick graph and see what that looks like. If I go to negative 3, 3, I have a point here. And these are going to be considered opposite endpoints, so I'm going to put point B. I have point C at positive 2, negative 1. This is point C. Since they're opposite to each other, we know that the circle is going to go like this. I can actually label this, and this won't be drawn perfectly, but that's our diameter, right? If I know the diameter, how can I find the circumference? Well, the formula is circumference equals 2 pi r, or circumference equals pi times diameter. So all I really need to do is find the length of that line, the diameter length, and then multiply it times pi. Again, to find this distance, I can use the distance formula because I have my 2 points, or I can do Pythagorean theorem. Since I have my graph here already, I'm going to draw a right triangle, and again, Pythagorean theorem, I have the lengths. The bottom length would be from negative 3 to 2 is going to be 5. From the vertical length from negative 1 to 3 would be 4. So if I do Pythagorean theorem, I got 4, 5, and then this right here is the diameter. So 4 squared plus 5 squared equals the diameter squared. That's Pythagorean theorem. If I simplify, we got 16 plus 25. 25 plus 16 is 41. To find the length of the diameter, I square root both sides. So the diameter equals control square root of 41, 6.40. That's my diameter. Now that I have diameter, I can plug it into my formula for circumference, and I have circumference equals pi times 6.40. and that's going to give us 20.11. Hopefully this feels like a review of what we've been doing in class and a bit of a review from middle school. The next one, feel free to pause it and try this problem on your own. Find the length of the diameter given the center and a point on the circle. Again, we have to start with the picture. Let's draw this image and let's see what that would look like. We're starting with the center is at 2, 1. This is point A. And it has the point on the circle for 4. 3, 4. Let's see. Let me draw it a little better. 2, 3, 4. 1, 2, 3, 4. So at 2, 1, I have the center. And the point on the circle would be at 4, 4. So if I imagine the circle, it's going to go something like this. From the center to the end point, we call that the radius. We're trying to find the length of the diameter. So there's two ways to do this. You can find the length of the radius and multiply it times 2. As you can see from up here, we have two relationships. We can multiply the radius times 2 to get diameter, or we can find the other endpoint where the radius would end, and we can then find the opposite endpoint and then find that distance. So the two options are, take this slope. We have this slope that we can emulate going this way. Let's see, 1, 2, 1, 2, and then down, 1, 2, 3, 1, 2, 3. We know it would end here if we did so. This picture could have been drawn better. Right? If I were to draw this a little better, we could have this could have gone through here, right? I can find the full distance by using this point and this point, using the distance formula or Pythagorean theorem, right? I can make a right triangle here and find that full distance. Again, this picture doesn't do it justice, but I can find that length knowing that the radius is half of the diameter. So I can use rise over run to locate the opposite endpoint. So let's zoom in a little bit here and let's solve this problem real quick. So if I'm doing Pythagorean theorem, I can see that the length of this line, 1, 2, 3, 4, 5, 6. This side is 6. The base over here would be 1, 2, 3, 4. And call that 4. And then that whole triangle overall would give me the diameter, and I can find the length there. So as you can see, zoom back a little bit, I have this right triangle that I created using the radius, right? I took the radius, I doubled it to find the diameter, and I know the length here is 4 and 6. I can use this to find the diameter length. So this is just Pythagorean theorem. We got 4 squared plus 6 squared equals diameter squared c squared. 16 plus 36 right? 36 plus 16 is 52. Square root both sides, and the diameter length is the square root of 52, which is about 7.21. Alternatively, you could have found the length of the radius and then multiplied it by 2, right? That would have given you a different triangle over here if we just focus on the radius. Find the length of the radius, and then that radius, double it to find the full length. Okay, let's go with a few more vocabulary words, do a few more examples, and we're almost done. As you can see down here, we have another vocabulary word that says a polygon is inscribed. Here's the key word. Inscribed means that the vertices of the polygon lie on the circle. Notice how this quadrilateral has all 4 points on the circle. It means that the polygon is inscribed. That's through the polygon's point of view. Through the circle's point of view, we can say that it's circumscribed. A circle is circumscribed about a polygon if it contains all the vertices. These two words really mean the same thing. It's just that one of them is from the point of view of the polygon, and one of them is from the point of view of the circle. Here's how you could say it. Quadrilateral MNP, LMNP is inscribed in circle K, or you could say circle K is circumscribed about quadrilateral LMP. All this is telling you is that whatever polygon they're naming, all the endpoints will be on the circle. And knowing this word, we can actually set up an additional set of problems. So let's try some out. So here we have a square with side length of 9 inches is inscribed in circle J. Inscribed. So I have some circle. I have a square, right? I can draw the picture here of a square. I'll draw that with a polygon. And then I have a circle, J. So I have some circle that contains all of those endpoints. This is J. Now the square has side length of 9 inches. So I'm going to label this and zoom in a little bit. I'm going to label this 9. The square, all side lengths are 9. Find the exact circumference. How would you go about finding the circumference of the circle given that a square fits perfectly in that circle? Well, what I would do is I would connect these endpoints through the center. And since this square is 90 degrees on all sides, cutting down the middle creates the diameter. This is really just the diameter. So if I can find the length of that line, which is the diameter, we would then have circumference equals pi times diameter. Now, since we're cutting a square diagonally down the middle, this is technically a 45, 45, 90 triangle. Right? Since it's a 45, 45, 90 triangle, the rules of a 45, 45, 90 triangle, if we think back to our second to last unit, these two sides are the same, and the diagonal would be multiplied by radical 2. Therefore, the length of our diameter would be 9 square root of 2. You could also do Pythagorean theorem if you wanted and just focus on a squared plus b squared equals c squared. But this is a 45, 45, 90 triangle, which can be done pretty quickly. Circumference equals pi times 9 radical 2. If I wanted to find the exact circumference, I could leave it in this form. Or I can put things in the calculator with pi being 3.14. And I can say this is just 3.14 times 9 times the square root of 2. 39.97. And this is inches because the square was in terms of inches. How does that feel? We're putting a square in there because it's inscribed. Cutting the square down the middle diagonally creates a diameter, which then forces you a 45, 45, 90 triangle. We use the rules that we know from 45, 45, 90 to find the diameter, the diagonal, the hypotenuse, whatever you want to call it. And that's just 3.14 times pi. Sorry, 3.14 times 9 radical 2. Let's check out this last example for us. As you can see here, we have two circles that end up intersecting and giving us multiple different radius or different lengths or different segments along there. We know that circle with center R, I'll do color-coded, so circle R has a circumference. So this circle has a circumference of 62.8. The circle with center S, I'm going to do this in red, circle S, has a diameter, that length, the diameter is 30 centimeters. I want to use that information to figure out what RC, DS, and CD are. What are those lengths? We can already figure out the length. Well, let's get this for a second. Let's look at circumference and find the length here. Find the length RD. RD is the radius of the blue circle, the smaller circle. Since the circumference is 62.8, we can set the circumference. We have a formula, right? Circumference equals 2 pi r. If the circumference is 62.8, we can set that equal to 2 pi r. Now, if pi is equal to 3.14, this is really just 62.8 equals 2 times 3.14. Since I have all the information there, I can just solve for r as my radius. So 62.8 equals 6.28 times r. Divide both sides by 6.28. The radius of the smaller circle is 10. So I know this length, I'm going to put this in black so we can see it better. From here to here is 10 units. Now, I'm not looking for RD at all here, but I am looking for RC. If you notice, I have these two circles have different length radius. Those radiuses, or radii, overlap. Since the diameter of the red circle is the diameter of the red one is 30, I can cut that in half and say that the length here is 15. The radius of circle S, this radius, is 15, while this radius is 10. How much of it overlaps? Well, we take 15 minus 10, and we see that 5 of it overlaps. I'll label this in maybe orange. So therefore, this length from here to here is 5 units. CD is 5. To find the length of DS, let's go to a different color. Let's do that in purple. To find this length, we know that the full radius is 15, and I just found out that this length was 5. If we subtract 15 minus 5, we get the leftover range, which is give us the length of 10 from here to here. So DS is 10. And now, as you can see, similarly, the length of RC, if the whole radius is 10, and we already have part of that here, it's just 5. How much is left over? 10 minus 5. You got it. That gives us that this piece is 5 from R to C. In the end, we needed to work backwards a little bit. Given circumference, find the radius. Given diameter, we found the radius as well. And then we figured out we have two circles that are overlapping a little bit. Subtract the radius to figure out how much is overlapping. And then from there, we found all the different lengths and different measurements. I hope this has helped. Please let us know if you have any questions. Don't forget to like and subscribe if you haven't already. And as always, we'll calculate later.